In this short video, we will talk about some basic concepts in mathematical analysis, more specifically in topology. First, we need to define several concepts. The first concept we will be defining is the function concept. We are using function all the time. A function in mathematics is often defined this way. A function maps two sets, set A to set B. We have a domain set and we have a target set. A function f maps every element in the domain set, any element for every element in a domain set A, the function f will map it to at most one value in the set of B. It means every value in the set of A must be mapped to at most one value in B. But B can have some elements that has not been mapped by any element in the set of A. So FA suppose is the set of all the mapped elements in B, in which case FA is a subset of B. It can be a proper subset, which means B may have multiple elements that has not been mapped by any element in A. Also, in this concept, we allow many-to-one mapping. That means multiple elements in A can be mapped to the same element in B. The converse is not true. That means an element in A cannot be mapped to multiple elements in B. So one-to-many mapping is not allowed. This is the conventional definition of function. In other non-conventional definitions, we can define multiple value functions, in which case one function can map one element to multiple values. But in most conventions, the functions do not allow one-to-many mapping. Next, we need to define a metric. We need to define some very important concepts in topology. First, what is a metric? A metric, from its name, means some kind of measurements that can determine how similar or how different two objects are. Suppose we have one set. We have a set A, and it has many elements in set A. Suppose there are two elements, any two elements, A and B, that belong to the set A. We want to measure how different or how similar or how distant A and B are. So we can define a metric. that can do this job. Here, given A and B, it will return a real number, which is non-negative. If it is non-negative and it is 0 if and only if A is equal to B. Otherwise, it's positive, strictly positive. This is the first property that a matrix should satisfy. The second property a matrix should satisfy is interchangeability. That means the distance between A and B should be the same as the distance between B and A. The third property of a matrix is some triangle inequality, which states the distance between A and B plus the distance between B and C should be at least or bigger than the distance between A and C. It's like the triangle theorem in geometry. Suppose you have 3 elements or 3 points, A, B, C. The distance between A and B plus the distance between B and C should not be shorter than the distance between A and C directly. It is very easy to understand, but this is not always true in all settings if it is not a metric system. For example, in chemistry, if B is some kind of state that is facilitated by some catalysts, it might be possible that going through the state of B will make the process faster than directly going through the process from A to C. So this metric is not the universal definition of all processes. We have this definition for metric just for the purpose of the rest of analysis. It is by no means a complete version of what types of phenomenon that is governed by physical law. Once we have defined the metric, we need to define some topological concepts. First, what is a neighborhood? A neighborhood in a set S for any point P, a neighborhood of P is defined as all the points or elements of Q such that the distance between P and Q should be less than R. Suppose the neighborhood has a radius of R, and R is a positive number, positive real number. That is the neighborhood of P. Obviously, P itself belongs to its neighborhood because the distance between P and itself is 0, which is definitely smaller than any positive number. So P itself belongs to its neighborhood, of course. Another important concept is limiting point. Limit point. What is a limit point for a set? Suppose P is a limit point in a set, or in a metric space. Remember, we are defining all these concepts in a metric space, which means the distance metric has already been defined, satisfying all three properties, as we discussed earlier. For limit point, it must satisfy this property. That is, for any limited point and for any positive integer, the neighborhood let me write down the neighborhood in a different way. The neighborhood of P should contain at least one element that is not P itself. So it must contain at least one element from that metric space, and that element is not P itself. If that's the case, then P is called a limit point for that metric space. So P is a limit point in that metric space as long as we can always find, well, I should say we should a set that belongs to a metric space. Remember, a metric space is itself a set with a metric defined on it, and it can have a subset, many subsets. For each subset itself, they can be a metric space as well. The reason is the metric defined on the entire metric space can be applied to a subset of the metric space as well. So the metric defined on the subset of that metric space is still valid, is still a valid metric. Therefore, the subset of a metric space is a metric space. Suppose for a point in a metric space, that point, the point P, the neighborhood always contain at least one element from a set S, and that element is not a P itself, then P is called a limit point for that set S. Otherwise, if it is not a limit point for a set S, then it is an isolated point. For for any element in a set S, any point should be either a limit point or an isolated point. Because if it is not a limit point, it is by definition an isolated point. The next concept is interior point. For interior point, in a set S within a metric space X, it means for point P, it has a neighborhood that belongs to a that is a subset of S. You can find a subset of or you can find a neighborhood that belongs to the set S entirely, which means it's a proper or subset of S. That means the point P, in which case the point P can be called the interior point. If for a set S, every point is an interior point, that set is called an open set, or that set is called open. If for a set all its limiting points or its limit points belong to the set itself, then it is called a closed set. If for a set S, every point is a limit point, and all the limit point belong to itself, which means it's a closed set. It's a closed set, and every point is a limit point. Then that set is called a perfect set. If by definition that a set S belongs to a metric space, and every element in that metric space is either a point in S or a point or a limited point of S, then S is called a dense set. If for a set, if there exists a point P such that every element in that set have a distance, every element in the set S in a set S, if we can find actually we can, for any element in the metric space, if for any element in the set of S, the metric between P and Q is smaller than a number M, then the set S is called a bounded set. So it is a bounded set. That's the basic concepts, some basic concepts in topology. Now we need to prove some theorems or propositions just directly derived from these basic definitions. First, if a set has a limit point, if a set has a limit point, then the set is an infinite set. The set contains infinitely many points. Here, points means elements. Why is this true? Suppose the set, a set has a limited point, but only has a finite number of points. Then we can derive some contradiction. Suppose the limit point is P, and we can calculate the metric between P and Q for all the elements in the set S. Why? Because it only has a finite number of points. The minimal of a finite number of non-negative real numbers is existing. Suppose it's R, then we can define a neighborhood P, maybe R over 2. In this neighborhood, there is no other point except P that belong to, except possibly P that belong to the set. Because every element in the set, let's see, we can give the set a name S for convenience. Every element in S has a distance bigger than R, at least R or bigger than R. And now you have a neighborhood that has a distance, element in that neighborhood has a distance to P less than distance of less than R over 2 to P, which means there's no such points in S that can satisfy this property. There is no overlapping between this neighborhood and the set S, which means P is no longer a limited point. That's why this is checked. This is correct. So this is correct, and we can safely use this. Before moving on, we also need to define some important concepts related to countability. Let's go back to the concept of function. We mentioned that function allows one-to-one, many-to-one mapping. Of course, it also allows one-to-one mapping, by which I mean if a function f maps set A to B, suppose fa is equal to B, not just a proper subset or a subset of B. It is, of course, a subset of B, but it's equal to B, which means every element in B has some elements in A that maps the elements in A to B. So every element in B should be mapped. In that case, we say F maps A onto B. F maps A onto B. Onto suppose for every element in A, it maps to a unique element in B, which means you cannot have many-to-one mapping. In that case, we say that this mapping is 1-to-1 instead of many-to-one. 1-to-1 instead of many-to-one. This means every element, for every element in A, or I should say for every element in A, for every element x1, x2 in A, fx1 does not equal to fx2. This means this function is 1-to-1. If a function is both 1-to-1 and onto, then this function is called bijective, which means every element in A is uniquely mapped to an element in B. And every element in B is mapped by some element in A. If a function is 1-to-1 and onto, then that function is bijective. We also want to define a relationship called the equivalent or if something is called equivalent, they have to satisfy these these properties. If A is called equivalent to B, then it must satisfy these properties. A equivalent to B means B is also equivalent to A. And A is equivalent to itself. So equivalence has a self-reflective property and semantic property and transferability. That means if A is equivalent to B and B is equivalent to C, then A is equivalent to C as well. These three properties makes the equivalence relation. Equivalent relation is defined on a set, and in this set, for every two elements, if they want to be equivalent, then they have to satisfy these properties. So an equivalent relation defined on this set means for every element or every two elements, they must satisfy these properties. Remember, a set can contain any element, which means a set can contain another set as its element, but it cannot contain itself as its element because it will make that set very weird. Let's see if we can define a set which contains itself as a subset. Suppose S is an element of S itself. Then that would be a very interesting set. Does it exist? It's likely, but not very likely. S belong to a set. S itself belong to a set itself. Let's see if S is defined recursively as itself, as an empty set. But empty set is not equal to a set that contains empty set. So in order to make the set contains itself as an element, you have to define a set with some recursive formula, which means for every element in the set is non-empty. Suppose for that non-empty set, every element, if there for every set, for every element, suppose that set S is not empty, it contains at least one element A, and for any A belong to that set, a set that belongs that contains A as an element also belongs to that set itself, which means if A belongs to S and the set containing A belongs to S, and this belongs to S, and so on. It can go on and on. But does that mean S belongs to itself? If S belongs to itself, it seems impossible. So let's do not dive into this even further. It seems to be some interesting question, but less significant. We may not need this for a long time. What we are going to do next is to define some countability. There is a natural set. In many cases, starting from 0. Here we define starting from maybe just from 1. If you define as starting from 0, that's not a problem. This is a natural set. If there is a bijection that maps the natural set N with a set S, then that S is called countable. Obviously, a set is if a set is countable, it's infinite because N is infinite. If a set is finite, it contains a finite number of elements, then it cannot be one-to-one mapping from integer or integer numbers to S. So if S is countable, then it can be mapped bijectively from integer numbers. And you can list the elements in S, S1, S2, S3, S4, one by one. And by listing this way, you cover all the elements in S. In fact, for a finite set, you can always list this way. If it is finite, then there will be infinite many duplicated elements listed in the way forward. If it is infinite and it is countable, then you can list uniquely. in a sequence without duplicating any two elements, any element. S is countable, but if S is not countable but infinite, can we find another set that is not countable? In fact, we can find many sets that are infinite but not countable, which we will discuss next. But first, we want to know if an infinite subset of a countable set is also countable. The answer is positive. An infinite set, subset of a countable set is also countable. How do you prove this? First, the subset A, suppose the countable set is S, and there is an infinite subset A. Of course, it is a subset of S, and it is infinite. And we already know that there is a one-to-one onto bijective mapping between integer numbers S1, S2, S3, and so on. This is a mapping for the countability of S. We know that there exists such a sequence that that lists basically all the elements in S, and one by one, and then there is no two positions which contain the same element. What about A? Can we list A in this way as well? Yes, we can. The reason is once we have this sequence S1, S2, S3, we can then test whether S1 contains S1 is in A, and then we test S2 if ST2 is in A, S3 is in A. We will eventually find the first element that is in A, and then we will encounter the second element that is in A, and so on. We will continue going through this process. We can find out all the elements that is in A eventually. And this process is infinite because there is an infinite number of elements in A. That means this sequence is also infinite, but it maps exactly to integer set 1, 2, 3, 4, and it is bijective. The first integer maps exactly to that exact Sn1 element. Once we have already defined the sequence S1, S2, S3 as the mapping for S between integer from integer set. In this case, we find a mapping that maps integer bijectively to A, which means A is countable. That means our assumption is correct, and this becomes a preparation. Next, if a set is countable and it contains and another set contains a countable number of countable sets. So there is a countable number of countable sets. So AI is a countable set I, the ith set, and AI is countable, and we have a countable number of such sets. If we put them together as a union, will that new set be a countable set? Or more generally, suppose there is an index, there is a set A, and somehow for every alpha in A, every alpha in A associates with a countable set B. If A is also countable or at most countable, which means it is either finite or countable, then will the new set, which is the union of all the set of B indexed by alpha in A, is countable or not? It turns out it is countable. Why is that? How can we find a mapping that maps the integer set to this new set bijectively? First, we can do this thing. We suppose B alpha is countable or at most countable for each alpha, or for each alpha, we can list B alpha in a sequence, in a sequence way. And we have this many alphas because we can list each set B indexed by alpha horizontally by their elements, and we can list all different elements in A vertically. And we can then count all these elements this way. We first count the first element in B1. Suppose alpha is indexed in an integer set. We count B1 1, then we count B1 2, we count B2 1, we then count B2 2, we then count B1 3, we count B3 1, we then count I should have counted B13 before B22. So basically, we are counting diagonally. We are counting diagonally. We are counting this way, this way, this way. And we can keep going on. By counting this diagonally, we can eventually map all the elements in S uniquely, or we can basically find a onto mapping. We find a mapping that is onto from integer to S. If S is infinite, then S is countable. If S is finite, then it is finite. If S is infinite, as long as N maps onto S, then it must belong to some countable set. And that is the concept of that is determined. The fact that S must be countable is determined by its definition. So why is the case that if N is mapped onto S, then N is then S is countable? The reason is that first, if S is mapped, if N mapped onto S, it means S can be a subset of some countable set. S is and you can you can map S in a new way. So suppose S is countable, is uncountable, and you find a mapping. And you find a mapping that is onto. But there are some positions where they both or all of them map to the same elements in S. How to address those issues? So you can find another mapping which is 1-to-1. How to do that? First, you find the first element. So you find for the first element, for the integer 1, you map to S1, which is in S1. Then for the second integer, you will map to whatever N is. It may be the second element, but it may be the third element, as long as that element is not included in the already mapped set. So you keep track of what have been mapped, and you only put the new element that has not been mapped. This process can go on and on. And if it won't terminate, then you find a bijective mapping between N and S. And that means S is countable. So here we have defined how to map S into we know that a countable number of sets the union of a countable number of countable sets is countable, or a union of at most countable sets is at most countable. This means if you have a set which contains a sequence of elements from another set, A to AN. So suppose all these elements belong to A, but you get a new set which contains elements from formulated this way, and all these individual coordinates in each of the element in B belongs to the set A. If set A is countable, what about the set B? It turns out B is also countable. The reason is, suppose only n is equal to 1, only one element is in this sequence, in this tuple, then of course every element in A is uniquely mapped to elements in B. In that case, B is countable as A, because countable is transferable. So if A is countable and A and B are uniquely mapped one-to-one onto, then B is also countable. Now we use mathematical induction. Suppose B n minus 1 is countable, and B minus 1 contains A1, A2 until AN minus 1, where n is bigger than or equal to 2, which means the first case is just the B1, which is just exactly first case. B1 is countable, and we want to deduct Bn, which contains A1 until AN as its element. Will this be uncountable? Yes. First, all these Bn, all the Bn minus 1 is countable, and then you basically have a countable set of Bn minus 1. So for the last element An, you can select any element from A, and then you have a union of all these new sets, which based on our previous proposition, it should be countable. So this tuple is countable. That's for now.